Hello everyone, my name is Tiva Albin and I'm the head of industrial automation at Embotech. Embotech is a startup based in Zurich which deals with real-time decision making. And today I want to give you an introduction to model predictive control. So what I will be talking about is, first I want to show what is MPC, and then I will look into two examples. First, autonomous driving, and then industrial automation, and we will look how actually MPC is applied in these two areas. So let's start with talking about what is actually MPC. So MPC is abbreviation for model predictive control, and if you look on the concept of model predictive control, so what you actually do is you use a model, and this model is actually a mathematical model, and this describes the system behavior. And you predict with this mathematical model, this system behavior, what you think it will be doing in future. And then based on these predictions, you actually calculate your control inputs, and you calculate these control inputs by solving an optimization problem. And you do that during runtime of the process, and you get a planning of control inputs that you would apply. So let's look on this picture here. So you have the past values with past reference values, with past control inputs and past measured outputs. And now you predict actually what would happen if I apply some predicted control inputs. How would actually my predicted outputs evolve? And the optimization problem actually tries, for example, to minimize the deviation between the predicted outputs and the reference values. And you set this task up as an optimization problem, and then you actually solve it. And by that, you get the best possible control inputs, for example, as I said, to be as close as possible with the predicted outputs to the reference trajectory. And what is done on top of that is you solve this open loop optimal control problem sequentially. And this is actually called receding horizon principle, because what you actually do, and that's what we see here, you plan for a certain horizon, but you only apply the first control action, and that's what you do, and you discard your entire rest of planning. And now here comes the receding horizon, because you shift this horizon, because now you have evolved in time, and you plan again, and you actually apply again your first actions, and you discard the planning again, and then you do it over and over again. And because you shift this horizon, it's called actually receding horizon principle. And if you do that, actually, because you always take into account your new situation, so this might be your system states, but also your disturbance values, you actually have a feedback control algorithm. And every time when you do this planning, this is an open loop optimal control problem, because you plan based on what you know of the future, and you solve it over and over again. So what are the main components of model predictive control when you design a control algorithm that you need to take care of? So you have the process model, and you need to have an explicit process model for prediction of future system states. And as I said, this is a mathematical model, so it could be a state space model or an ordinary differential equation system. And so you as a user, you have to actually have this process model that describes your system. Then at the same time, you need to have a formulation of your optimization problem. And because the optimization problem at the end determines your characteristics of the control. And so you need to think of what are the requirements for your control algorithm, and based on that, you need to appropriately formulate this optimization problem. So now we have the process model and the formulation of the optimization problem. And as I said, typically what is done during runtime of the process, you solve this optimization problem. And so you need some numerical solution algorithms, which is called solver, that calculate the control inputs based on the solution of the optimization problem. And these three components are the main three things you need to think of when you actually design an MPC algorithm. And as you can already see, depending on the system you want to control, you might think of different ways to actually having the solver or the process model or the formulation of the optimization problem. So the biggest challenge is actually real-time feasibility, because you typically have very small sampling times, and you need to be sure that you can actually solve your optimization problem in this time frame. And if you would have a very complex process model, of course, the optimization problem would also take quite a lot of time. So you need to make sure that for appropriate control, all of these three parts, that they fit and that you actually are able to deal with it. On the other side, if you have a very simple model, it might be actually too simple because you not describe appropriately what your system is actually doing. And what is actually the reason that we do this optimization based, and let's call it in general decision making? So we have this decision making problem, and what you would do, and what is the standard in the industry still, is that you translate your task into some control software. And in some cases, this might be that you have a lot of if-else statements, and depending on what happens, you actually change it. Might be also lookup table-based controller, where depending on the operating point, you also change your parameters. But it is very, very dependent on different states. And then your software needs to take into account this state-dependent behavior. But what we think is going to be the future is to specify actually your tasks, your engineering tasks, where you want to solve your decision-making problem, that you specify this as an optimization problem and then solve it actually. What is the big benefit? Like looking on a very high level on it, if you have a task that is quite easy, then you are actually better with dealing it in the fashion to translate the task into control software. But if the task gets very complex, then actually your solution complexity will exponentially increase. And if you have put it as an optimization-based task, it will just linearly increase. So it's, if you have these very complex problems, it's much easier to solve them with optimization-based methods compared to the ones that are currently available. So let's look at the two main applications, I would say, of model predictive control. So the first one is actually motion planning. So you have, let's say, for example, autonomous driving, where you have a car that you want to drive autonomously, or you have a robot that should be operated autonomously. And the task is to go from A to B, and you have obstacles in the way, and you need to find a motion plan. This avoids, for example, the obstacles. In some applications, you have on top the requirement that you want to be as fast as possible. Or in others, you might want to go there with low excitations so that it is comfortable. And you need to find the best way to go from A to B. And at the same time, you always need to take into account that the obstacles might change actually during runtime. So if you think of a car which is driving on a highway, then you always have different situations. So you need to constantly update this motion plan. And here also MPC is a superior method to actually deal with these kinds of problems. Another one, so that's the very classic one, is reference tracking control problems. So what you have is you have a reference value which should be set point tracked, and you have some plant that is to be controlled, and you measure actually your values that are the outputs of the plant. You feed them back compared to the reference values, and classically you would do that with a 2 degree of freedom controller. So you have some feed forward control action, and you have some feedback action, for example, a PID controller. And if you have a nonlinear system, then that you want to control, then you typically, one way to deal with the nonlinearity is actually to use lookup tables, and then your parameters KP, Ki, Kd, they get operating point dependent, and the same holds true for the feed forward control. So you have operating, or for example, reference point dependent feed forward actions. If you now substitute this by an MPC based controller, then you don't have the division between feed forward and feedback anymore, but you replace it actually by the MPC, and the MPC contains the process model and then the optimization algorithm, and this calculates actually your control inputs. So to show you just that the MPC-based approaches, that they are capable of solving more complex problems than you would be able to do with standard approaches, I have one example. So a classical control example is the inverted pendulum, where you have a card and you have a pole on the card and you try to balance this on the upright position, and which is unstable. And now what you can do with MPC, so we have this position A here, and we assume that we have some obstacles, which are shown by these black marks. And we want to go to B, and we want to go from A to B actually in a time optimal manner. Then I can show you what the MPC-based solution actually makes. So it takes into account that there is this obstacle, and in order to go from A to B, you actually at the very beginning, which might be counterintuitive, you have to drive backwards, and you see it systematically takes these obstacles into account, and it just goes exactly to the lowest point and then goes from there to the point B. And so we are really optimal in how we go from A to B. And this is of course very complex if you want to solve this with an PID-based controller. And if you assume like this obstacle, you would just increase it. In an MPC-based fashion, you just increase the parameter of the obstacle, and then you have the algorithm. In a PID-based setting, you might to retune your whole algorithm again. So let's look a little more in detail what are the advantages and disadvantages of model predictive control. Actually, because we take into account the model and then do this optimization, we are actually quite flexible in terms of the system behavior that we can actually consider. So we can actually consider time delays, multiple inputs, multiple outputs, means you have several inputs that control several outputs. You can control non-minimum phase behavior, non-linearity, and a lot of other features because you actually model them. And as long as you can model them and you're able to optimize for them, you can take into account of them in a very systematic way. And then as we have the optimization problems, we are also able to include constraints. And these can be constraints on the inputs, on the states, and on the outputs. And MPC, that's like the biggest advantage compared to other classical algorithms, that you can actually systematically take these constraints into account. If you take the system behavior, for example, depending on the system behavior, there are different control algorithms which take care of them. For example, if you have time delay, you might take a Smith predictor and so on. So there's different ways to deal with it, but with MPC, you are very systematically able to do it. You don't need to have several features, and you can at the same time consider the constraints. What you can do on top is you can consider future desired values. So if you know that you in future there's some disturbance values upcoming, or as in the case of the motion planning, there's an obstacle in the future, you can easily include or consider these desired values. And as said, like classical control, I use feed forward plus feedback. Here, the feed forward control is inherently included. And because, going to the next point, because we do set this as an optimization problem, we have the tuning in the time domain, which is often more intuitive than tuning the control algorithm in the frequency domain. And because we are able to take the nonlinearity into account, the time delays and so on, we actually can have a very high control quality. And because we do take into account directly the nonlinear system behavior, for example, so we have also low calibration effort. Just think of it, if you have a very nonlinear system and you need to tune for it at different operating points, then this is much more tedious as if you just insert your nonlinear system behavior and directly use it. And the last point is the possibility to reuse models. So let's take the example of motion planning. So if you have a vehicle dynamics model, then even if you change your vehicle certain parameters, for example, tire coefficients, you can still reuse the entire model without the need to come up with a completely new control algorithm. And this is sometimes the case. Assume you have one system which has no time delay, but then you include a new actuator which has some time delay. It might be that you need to entirely change your control algorithm. But with MPC, we just include the time delay and then we can still use everything else. So you see there's a lot of advantages with model predictive control, but always when you have advantages, there's also some disadvantages. One disadvantage is you need to have the process model, and this needs to be a control-oriented process model. So what I mean with it is if you have some models that are computational fluid dynamics, where you have a lot of states and partial differential equations and very high complexity, then it's too complex to actually solve an optimization problem with it. So we need to boil it down so that it has limited complexity, but it's still able to actually represent your input-output behavior. Then compared to classical algorithms like PID-based control, you have a higher computational effort. So it might be that you need to have a better hardware to actually run it on an embedded system. And the third point is you need to be very robust in terms of your numerical algorithms so that you find always a suitable solution. Because with the PID-based control, you know that you always have a suitable control action. And now that we deal with numerical algorithms, we also need to make sure that we always find a suitable solution of the optimization problem. And then the last point, this correlates to what we said before. So real-time feasibility is a challenge. And this is especially the case when we deal with complex models and at the same time have small sampling times. Then you really need to make sure that within the time frames that you have, that you are able to actually solve your optimization problem. Good, so let's look at the types of MPC, because MPC now I called it a control algorithm, but actually instead of actually being one control algorithm, it's rather a family of algorithms. And depending on what kind of model you have, what kind of optimization problem you have, there's actually different names for it and different concepts also behind it. And here are just the most prominent ones, which I put on a slide. So if you have a linear model that you take into account for prediction and you have also linear constraints, then it's typically called linear MPC. If you have now a nonlinear model or maybe nonlinear constraints, then it's called nonlinear MPC. One way in between linear and nonlinear MPC is linear time variant or adaptive MPC. So some people use the name linear time variant MPC, others use the name adaptive MPC, and there you have in every time step a linear model, but this model changes from time step to time step. Then you could have hybrid MPC, where you not have any more a continuous model, but you have a prediction model which has integrated logics and dynamics. And then you need to solve mixed integer problems. Then you might take into account stochastic information. So you have a stochastic prediction model. This is called stochastic MPC. If you have uncertainty in your prediction model, typically linear models are used. Then you have a robust MPC. And what you can do as well is, instead of solving the optimization problem online during runtime of the process, you calculate your control law offline and you save just this control law, and then you just execute your control law online. And this is called explicit MPC. And the last one is called economic MPC. And there you calculate your economic manipulated values. So instead of having a stabilization process where you want to reference track and have a stable system behavior, here the focus is rather that you have some control inputs that operate your process in a very economic way. Good, and I just want to show you, like to give you an impression of the differences of the types of MPC, just a classification of linear versus linear time varying or adaptive versus nonlinear MPC. And so we have two axes, the computational complexity and what your controller is actually capable of doing. And if you have a linear time invariant model, then your computation complexity is very low. So you can solve it very fast. But on the other side, your controller will also only be able to handle linear systems or nonlinear systems that are not too complex. And in this case, you actually solve in each sampling step a quadratic program. And these can be solved quite reliably and also quite fast. If you want to increase a level of complexity, so that you are capable on the one side to control more complex systems, but with the drawback of being computationally also more complex, then you can go to linear time variant, or as I said, also called adaptive MPC. And here you have in every time step a linear model, but it still results in a quadratic program to be solved. If we now go into nonlinear MPC, then you have a nonlinear system model that you are looking at. And in this case, you solve actually nonlinear programs, And there's two ways to deal with it. And you can either, in each sampling step, just calculate a suboptimal solution. So you don't converge your optimization algorithm to the end. And one method that is often used is that you solve only one sequential quadratic programming step. And this is often called real-time iteration scheme. And in this case, you have a little bit higher computation complexity, but you can already control more complex systems. And often this nonlinear suboptimal solution you can use actually if you have reference tracking problems. And for these, they are quite suitable actually. And the other case is that you have a nonlinear system model and you converge in every iteration step to the fully converged solution. And this is often the case in motion planning problems where the suboptimal solution is not enough, but you really need to converge. And then you have the highest computational complexity, but then your controller is also capable of doing or dealing with very complex systems. So let me give you a summary. So MPC-based algorithms, they are superior in terms of the control quality. You can handle constraints in a systematic way, and you can handle very complex system dynamics. But on the other side, a major challenge is the real-time feasibility, and your control performance depends strongly on the quality of the model. All right, let's now look into some application examples where actually model predictive control is applied. And for that, let's start with a little bit of history of MPC. So going a little back in time, so around 1970, actually MPC evolved in the process industry. So for example, you had chemical plants which were controlled by model predictive control, and it was a great success story there, and it got implemented in more and more applications in the process industry. And these were actually applications that were characterized by rather long sampling times and small or slow dynamics. And the nice thing is in the process industry, you can have still some quite powerful computing units to actually calculate the active values. So it was quite nice environments to actually apply MPC. And still you had a lot of gain, because if you are able to increase the productivity in such a chemical plant, and of course you have a lot of money that you actually will save because you are operating the process, for example, more efficiently. If you now look into examples of applications from today, then these are actually fields like autonomous driving, robotic motion planning, CNC machines, or guidance and control for aerospace systems. And what are characteristic of these examples are actually that the sampling times are very fast, so very small sampling times, so you need to compute very fast. At the same time, it's often embedded systems, so you're not able, or you need to be capable of solving the whole problem with this limited hardware that you actually have. And one other big distinction from the early developments of MPC is in the process industry, you still have an operator who's sitting there, and you exactly know what is happening. What I mean with that is you have a set point which you need to follow, but you know exactly what the set point curve looks like. If you take autonomous driving, you don't know in advance what actually the driver will be doing. So you need to be capable of handling any reference change that is actually upcoming. So meaning that the applications that are at the moment evolving, or where it is actually applied, they are characterized by the need of very high reliability and the limited hardware where you need to compute everything on. Let's look a little bit more in detail into two example areas. So autonomous driving, and then on the other side into smart factories. Starting with autonomous driving, one key point for autonomous driving is actually being able to handle the vehicle dynamics. And you need to be able to handle the vehicle dynamics due to different reasons. The first one is safety. So you need to be capable of driving the vehicle at the physical limits. So you always want to have a stable behavior so that you're safe. And this is even more complicated when you have a setting, as you see here in the picture, where we have a truck where you drive high speeds with a trailer, and then the vehicle dynamics gets even more complicated. At the same time, you want to drive very comfortable. So assume you are oscillating around, then you would actually get motion sick. That's what you not want. Instead, you want to have or offer the passenger a comfortable ride. Then the third point is you also want to give the driver a certain driving experience. So let's assume you have a sports car, then you want to use also what you have in terms of car capabilities. And you see like these requirements, or these different aspects, let's call them, they are quite complicated to satisfy at the same time. And here, in this case, MPC and mathematical optimization becomes very crucial because you're able to actually fulfill all these requirements. And MPC mathematical optimization will be in every autonomous driving stack, because with classical controllers, it's very, very hard to comply with all the different aspects. So now you might say vehicle dynamics, that can't be so complicated to be able to deal with it. But now let's look at this video where we see actually how complicated it can be. So you see the cars that are sliding around the corner. And so it seems the human driver is not always the best at knowing the physics and knowing the limits of the car. And of course, if you have an autonomous driving car, then you want that the algorithm knows these physical limits and is capable of still driving safe even in these scenarios. I will show you that MPC is capable of doing that with 3 different scenarios. Let's look at the first one. And this is done by AMZ Racing, which is an ETH Zurich student club for racing. And they use actually a forces-based motion planning algorithm to drive an electric car. And they actually have won a competition with that. And they're able to steer around this at the various corners and handling the car dynamics in a very nice way so that you're still able to have a top performance. The second scenario I want to show, it's also a forces-based motion planning algorithm. And there we have a commercial vehicle, and it's also driving autonomously. And in this case, there's an obstacle placed. And you only see in the last minute actually that there is an obstacle. And due to the update rates of the MPC algorithm, actually the MPC algorithm can actually calculate an evasion maneuver. And you just saw, like if you would just brake, you would actually run into this obstacle. So the only way to be safe is actually to avoid it. And this can be done in this way. And this was a cooperation of Embotech and ThyssenKrupp. As last scenario, I show you a motion planning algorithm, which was also developed forces-based together with Einride, which is a Swedish startup that actually builds pods, electric pods, that actually are able to autonomously deliver goods. And here you see the Top Gear track. So it's from a British TV show. And they are actually also autonomous, the pod is driving autonomously. And with the motion planning capabilities, the MPC based, it was actually able to set a record lap time on this Top Gear track. And here again, different vehicle configuration, but still you are able to take the dynamics of this vehicle into account. And then you are able to actually drive optimally around this lap track to be, as this was the goal here, to be minimal in time. But the beauty, of course, of model predictive control, as you see, it doesn't matter if we have the electric driving racing car, or the standard vehicle, or the spot here. You can actually model the vehicle dynamics of these systems and then plug it into your algorithm, and then you're capable of actually solving these motion planning problems. Now let's look into industrial automation and where MPC can be applied there. And let's look specifically into smart factories that are more and more evolving. And if you have these smart factories, what you actually want to do, what is your goal at the end as a manufacturer, you want to be as productive as possible. So you want to produce as many goods in the lowest time. So you want to reduce the cycle time. Cycle time is the time that you need to produce a good. And at the same time, as the products get more and more complex, and you get more and more variants of products, you want actually to be able to have a batch size 1 production. So it means even if you change all the time your product that you produce, you want to be good. So what you don't want to do is that you have a lot of change time, and then you need to set everything up again, and then you produce a new part. But you want to get it down that you have an autonomous production systems, and it doesn't matter how big the batch size actually is, you still are very productive. The last part is you want to be very flexible. So even if you have varying requirements, because you have different products that all have specific needs, or you're changing your environments, that you're actually capable of dealing with this. And here again, the MPC, a mathematical observation, is actually an enabler for these kind of smart factories. And I want to show here again some scenarios. So the first one is also a forces-based solution, which we developed together with Bistronic, which is a laser cutting company from Switzerland. And here we use it actually to control CNC machines. And in this case, there is a redundant axis. So you have one movement which you can actually do with 2 different axes. And the 2 different axes, they have different characteristics. The one is very fast, but you can only move it a certain distance. And the other one, you can move over a long distance, but this is a little bit slower. And now the question is how to optimally split the movement along these 2 axes, so that you are on the one side that you are really fast, but of course, as it is about cutting, you need to be at the same time very precise. And this is what we did also with an MPC-based solution using Forces Pro. And there we were also able to actually increase productivity by up to 10%. And this allowed the laser cutting company to actually deliver a solution which is much faster as what their competitors actually have. Another very interesting topic is robotic motion planning. Also here again, as I said, it gets more and more flexible, and you want to be able to do the robotic motions more and more non-static and in a more dynamic way. And let's look into one example, which is motion planning with a linear axis. So what we see here is we have a manufacturing process, and you have a shelf with something which you pick out, and on the way you have some obstacles. And just for demonstration purposes, these are now some spherical obstacles. And what you want to do, or what you be able, is actually if the environment changes, because the cell has a new structure, that you actually update your motion plan, and that you can continuously run this operation even though the cell is changing. And you saw in this case, you are in a few seconds, you are able to actually recalculate the best path to get time optimally from the shelf to the manufacturing place. And another example where it gets even more complicated is if you have 2 robots that work together in one cell. So this is collaborative bin picking. So let's look at this. So you have 2 robots here. And as I said, you want to increase the productivity and reduce the cycle time. And the main bottleneck here in this cell is the the manufacturing place here in the background, and you want to use that as much as possible. And what is done to actually realize it is you have two robots that work synchronously, and you need to plan the motion so that they optimally do their task. And what they do is they pick out of the bin a metal sheet, then they do some alignment on this alignment station, then they do the manufacturing process, and the manufactured part then gets deposited into this bin. And you see now the motions of the two robots are calculated such that they are optimal, and then as a result we can use as much as possible the manufacturing place here. And if you would only have one robot, you would spend quite some time to go around, but not actually with manufacturing the part. And for this, of course, this is MPC also again, but here you need to take into account both robots so that you have a motion plan that takes into account what the other robot is specifically doing. And that you have a joint movement that is optimal in time, but where you don't collide into each other. All right, I hope I could give you a little bit of an impression what current topics for model predictive control are. And I think there's more and more topics upcoming. So I think we just see now the first versions of let's say MPC for embedded systems, and there's much more to come. Thanks.